Hello guys, in this video I'll take a look at Qwen 3.627b model and see how it will perform on a typical data science project. So this model is a dense model, which means all of the 27 billion parameters are actively involved in the token generation stage. And this supports both vision and text as input and can generate text as output. For reference, here's the settings I've used for Llama server. So the quant I've used is the Q4KXL from Onslaught. And by disabling the multimedia projection, I was able to get context size of about 90,000 tokens in my RTX Pro 4000 Blackwell GPU, which has 24 gigabytes of memory. And I'm also using MTP with these token sampling parameters, the temperature of 0.7, top P of 1, top K of 20, and so on. So you can pause and take a look at the settings. Maybe you might need to tune for your own hardware, but for this CPU, I got the best performance using these settings. For today's demo, I've set up this simple e-commerce website using Django, and we have about 43,000 products in the database. And for this task, we will improve the existing search feature that we have here. So the current algorithm just uses the query and checks whether the query is in the product title or not, and then returns those matching products just using pure SQL. But this is obviously not a good experience. For example, if I search for chair, then I get these results because the word chair appears in the product's title. But if I were to change or add more words, then of course this will not work. So for example, here we have wide armchair, wide velvet armchair. But if I were to just search for wide chair, this would not work because the characters that I have in the query, wide space chair, does not exactly occur in any of the products in the database. So we'll be using Qwen to figure out how it can improve the search feature that we have. To see how Qwen will develop and what the results look like later on, we need some way of evaluating the results or the rankings, right? So beyond the test cases that we have in typical software development process, for these kind of things, we need a separate data set, just like we do benchmarking for LLMs, right? So we have so many benchmark data sets that they evaluate the LLMs on. For example, for coding tasks, for agentic use cases, for reasoning, mathematics, and so on. Similarly, for this kind of retrieval task or information retrieval, search, however you want to call it, there are also benchmark datasets that we can use. And the products that you see here are actually from this dataset called WANs, released by Wayfair. And what this dataset is about the benchmarking and evaluation of search engines. And basically, they have about 43,000 products in this dataset, which I've already populated in our demo system. And for training and evaluation, they have also 480 queries. And for each of those queries, they also have some relevance judgments. So in the dataset, how the query and the judgments look like are as follows. So we have this query dataset, which has query ID, query, and query class columns. And for example, this query, salon chair, has query ID 0. And now in the relevance dataset, what we have is for this query, the query ID 0, the product with this ID is a exact match or the most relevant. And similarly, the product with this ID is irrelevant, and so on. Like there are some products which will be relevant for this and some irrelevant. And there are also some products which are partially relevant. So what we would like the Qwen to do is develop a system where it can show the relevant products before partially relevant products, which in turn are shown before the irrelevant ones. So there is an order to how you display in the search result page. So we have this query and relevant judgment dataset. What I've done is split that dataset into three parts: train, valid, and test set. And in this project folder, I only have the training and the validation set. And the test set is completely in a different folder so that the Qwen cannot see what is in the test set and cheat on it. So it can only access the train and validation set and then iterate whatever it's going to do. And based on the findings from hopefully the validation set, it will present me the best approach that it thinks it can do. And then I will evaluate that on the test set. So the idea here is that the Qwen model will then implement a subclass of base search with whatever approach it comes up with. And also in order to train the models or any artifacts needed for retrieval or ranking in the training class. So this base search trainer must be subclass, and it will implement maybe some things to set up, then train, and then save those artifacts in the disk. And before we start, let me quickly show you what the performance right now looks like. So as I already showed you, we have this relevance data given the query. For every query, we have the relevance data. And when we have this kind of data, we can compute or evaluate our strategy for the retrieval and ranking. And here's one result that I have. This is the one. So what we can compute are the following metrics. The main one will be the recall for candidate generation or the retrieval stage. So this is the most interesting metric for the retrieval part. And then for ranker, we are mostly interested in NDCZ. Depending on the use case, you might be interested in other metrics such as precision or MRR or mean reciprocal rank and so on. So here I have the number of queries in the test set. So this report is based on the test set that I have in a separate folder. So there are 48 queries, and for the recall at 100, so out of 43,000, the retrieval stage gives 100 products, and from those 100 we calculate the recall. And so here the recall at 100 is 0.04, which is pretty low. So the range of this metric is between 0 and 1. So 1 means the best, 0 means the worst. Similarly, the NDCZ is at 10. So we look at the top 10 results returned by the ranker and then compute the NDCZ on this. So this will be my primary metric here, which is right now 0.19. Again, this metric ranges between 0 and 1, 1 meaning the best, 0 meaning the worst. Then another kind of interesting metric to measure is also the empty recommendations. In this case, what this means is for these queries, in how many cases were we not able to return anything at all. So that means the recall or the retrieval stage had recall of 0, meaning empty recommendations, right? So there was nothing to rank at all. And similarly, we also need to figure out like what's the latency, because we can't implement a very complex approach which will take seconds to compute. So right now the baseline is at 44 milliseconds, and for this demo I'll ask the Qwen to make sure the latency is less than 100 milliseconds. It's just a random latency that I chose, but of course depends on the application that you have. Now I will give the Qwen model to investigate the dataset, investigate the code base, and then do EDA, exploratory data analysis, and then come up with a strategy to implement both of these, the retrieval and ranking, and then let's see how it performs. Okay, so here I'm using open code, and I already sent a message to Qwen just to test it out. So it's working. I get a reply. Let me clear this session, and I will paste the prompt that I have. So here all I'm saying is explore the code and the data and need to do the EDA, then come up with a plan to implement. And then I also give it a goal. So the goal is to increase the NDCZ at 10 and also making the empty recommendation less than 2%. while keeping the latency less than 100 milliseconds. So this is the constraint I'm giving it. And in this project, I already have installed catboost, scikit-learn, and pytorch, so it's free to implement whatever it thinks is the best. I'll just let it run, and once it has something interesting, I'll come back. Okay, so far it created two scripts to do EDA, and it took about 4 minutes. I think we started at 1845, now it's 1849. And in the part one of the EDA, it explored the dataset, the label distribution, then the query class distribution. It's analyzing the query about the word count, character length, and it's also exploring the vocabulary. Then it's looking at the baseline deep dive, so it's checking how the existing approach looks like. And it's also checking the performance on different query classes. So the query class, they come in the dataset itself. So they have assigned this query class for every query in the dataset, and it's using this to figure out for which query class the baseline is better or worse. Of course, during our production use case, the query class won't be available, right? So we only have the user's query, but not the query class. So this will only be used for the analysis. And in the part two, now it's looking at the product catalog. So it's checking not null percentage for every attribute the product has, for the name, class, category hierarchy, and so on. Then it's also looking at the product's name to figure out the average number of words, the length, and so on. It ran part 3, and here it's trying to figure out what kind of retrieval strategy will be better. So for now, I will not go into what it did. It completed all the EDA that it wanted to do, and now we have a report that it wrote to this file. So let's quickly look at it. So here it has the baselines information about like what the existing metrics are, and also about the dataset. And here are the findings. So here it figured out that using TF-IDF, or term frequency inverse document frequency approach, would result in a significant improvement in recall. Okay. And it also analyzed every query class and then saw where it had the most improvement. So in case of dryers, it seems we go from 0 to 0.84, which is a significant jump. And based on its analysis, it seems the product description does not add any meaningful improvement. And its fourth finding is rating signals are weak discriminators. Okay. And the next finding is query class and product class mapping is a strong signal. Okay, I think this is a wrong direction to go, because the query class, as I mentioned before, will not be available to us during the actual production use case, because from the search bar in the UI, the user will send a query, and the query is the only thing that we have when we do retrieval and ranking. But the query class itself, it was just present in the dataset, but it will not be available to us, right? So whatever it's trying to do with this query class, it's basically useless. And according to this guy, TF-IDF retrieval is fast enough, yes. And the final implementation plan is to have a two-stage pipeline. One, the TF-IDF for retrieval, then use a cat boost ranker. Okay, let's go to the ranker part. For a cat boost ranker, so it will train a ranking model, and for this model it will use these features. Let's quickly go through them. So TF-IDF similarity, okay, token overlap ratio, query in name, query in class, query in hierarchy, class match. Okay, this one, of course, this will be useless. And then we have other features about number of tokens in the query, the length of the product, whether the product has rating at all, and what's the average rating, then bin rating count, okay, for the popularity proxy, and max unigram similarity, best single token TF-IDF, okay, partial match signal. Overall, it looks good. And let's take a look at what kind of model exactly it's going to train in CatBoost. So it will be using a point-wise framing. Point-wise framing is a bit older or simpler approach. There are other techniques like pairwise or even group-wise. Pairwise and group-wise have been shown in many papers to be better than the point-wise approach, but let's see what we get. Our goal here is just to beat the baseline that we have, and using whatever it has suggested so far will already give a lot better results. And for the loss function, it's going to use a multi-class or root mean square error for regression on gain values. So the gain values meaning for each of the labels, it's assigning a numerical value, right? So either it will use this as a regression task or as a multi-class classification task where the classes are these three: exact, partial, or irrelevant. Let's quickly take a look at the training code it wrote. So we have the train function here. And the most that I'm interested in is the model and the training part itself. So it decided to go with the root mean square loss function, which means it's treating this problem as a regression problem. And it is using the evaluation set and using the early stopping. So this is actually a good decision that it took, that we have the evaluation set and to use it to do early stopping as well. Just finished the training and now it's running the evaluation on the validation split, of course. Let's see, what do we get? Okay, the reports are in here. Let's quickly take a look. Oh, okay. It also ran the command to compare the two implementations. This will be much easier. So the substring source is the baseline, and this is the one that it created. And the empty reco is 0%. Okay, this is very good. Then for the recall, we have 33, 0.33, much better. Recall at 50 is another metric. We are not looking into that. Then let's go to NDCZ at 10 for Anchor. 0.63. This is a lot better than the 0.19 that we have in the baseline. And for the latency, let's look at the P95 in total. This is quite bad. So it's taking 626 milliseconds. Hopefully it realized that the latency is not that good. Okay, it changed something here, and the new report says the latency is 25 milliseconds compared to 600 something that was there before. Okay, so I ran the evaluation on the test set, and here are the results. On the left hand side is the baseline, and on the right hand side is the one from Qwen. And in this test set as well, we have 48 queries, but these are different queries from the one that we had in the validation set. And as we can see, the recall now is 0.38 compared to 0.04, which is a lot better. And also for the NDCZ, now we are at 0.65, which is also a lot better. Empty reco 0%, good. and latency at P95 is also 25 or 26 milliseconds here. So overall, I think it has done a pretty good job. It explored the data set and then came up with the training and evaluation approach. And finally, we have this result. This model seems to do pretty good in these kind of tasks where we have the goal, and the goal had the constraints, right? The recall should improve, NDCC should improve, latency should not be more than that. So given those constraints, it was able to iterate as well. Like before, we saw the latency was 600 something milliseconds, and it knew that the latency could not be higher than 100, right? So then it updated some things. Now we're back to 25 milliseconds. And given these kind of scenarios like data science or machine learning tasks where the model can evaluate its own implementation easily, then I think this is a pretty good job. Now I've set the default source engine to the one that Qwen just implemented. And let's try out the queries that we tried before. So one is the chair, and it's a bit different than before. Here we see this chair. It seems to have more, the chair word is frequent in this title. So I guess that's why this ranked quite higher, because of the token overlap count. I think that's the reason. Yeah, so let's try the one that failed before. We didn't get any results for wide chair before, but now we see that because it's using the tokens or the individual words as also the features, the wide token also appears here. Similarly, the chair also appears here. Now, based on this logic, it can now retrieve these products, which the previous one was not able to. So overall, I think this implementation is pretty solid and can be used for any project that you have as well. Like, so you have a simple retrieval stage with TF-IDF and a ranking stage with cat boost. Of course, you need some kind of training data that you need to prepare. But overall, Qwen did a fantastic job here. So that's all I wanted to show today. Hopefully you found this useful. See you in the next video.